First of all, of course, I'm very grateful for the opportunity to talk here and honored by the invitation. It's very pleasant to be among colleagues. Now to the subject of my talk. What I'm going to do, what I did for a while and what I'm still interested in is, yeah, it's visible, right? I mean, what is the function that I'm going to study is right here. It is a function of two real variables. That's, beautiful R. The summation is taken over all integers, positive and negative, avoiding zero. Yes, can you zoom it? Yeah, one can zoom. Okay. Okay.
Now you have to move the sheet.
Right, yes, yes. So here is the function, okay? It looks as follows. It's e to the pi I t n squared plus 2xn, that's in the exponent. The whole thing is divided by pi I n squared. And after its summation is taken over integers n, avoiding zero. Now, actually, I wanted to study this function for the following reason. You know, this function is a particular solution to the Schröedinger equation of a free particle, and this equation is written here, for which the initial, the Cauchy initial data value problem is posed. And actually with a very simple initial data. The initial data is this, well, function here, r of 0x, that means f for t equals 0. We simply plug in t equals 0 into now our exponent here. And we get the function which is piecewise parabolic on the period. So it has only one singularity for x equals 0, where the derivative breaks down. So actually this is definitely a discrete oscillatory series on top of this sheet here. And the denominator is n squared. Now lately I got interested also in its kind of, generalization, where the exponent 2 in denominator is substituted for alpha. And actually, the only restriction which a priori has to be imposed on this parameter alpha is that alpha should be bigger than 1/2, because otherwise, this is really a bad series. It is not even a Fourier series, not interesting case. And let us also formally remark that, well, if I do if I differentiate formally, term-wise, this series in x, then this h function arises, which is the principal value sum of this kind. And definitely it is this discrete oscillatory Hilbert transformation, because all n's participate positive and negative with the quadratic phase. Now, actually, so definitely these functions, they satisfy Schrödinger equation that I just mentioned, and that I just wrote out. And the solutions to these equations, they are interesting, and particularly these functions are interesting for the following reason. Let me, provide the reasoning. Actually, the Riemann, Bernhard Riemann, according to the report of Karl Weierstrass of 1895, suggested this sum of sine series, like sine of pi n squared t divided by n squared, as a possible candidate for a function that is obviously continuous, a function of parameter t. But he conjectured that this function does not have any derivative anywhere. That he never published anything on this issue. But well, you know, Karl Weierstrass recalls this thing quite definitely. And actually, you know, it took quite a while to, you know, consider this function in full. That's what Riemann conjectured, and actually the full solution is due to Hardy and the paper of 1916 and Joseph Gerver of 1970. Actually, what Hardy proved that indeed the derivative of this sine series with quadratic phase does not exist at any irrational point, or at a rational point, t equal a over q, you know, that's a notation for a rational point. Of course, reduced fraction, where the numerator and denominator are of different parity, so the product of a and q is an even integer. He proved that, well, you know, really at such points, the derivative does not exist. And it was only in 1970 that Joseph Gerver proved that in all other points, that means rational points where both numerator and denominator are odd numbers, the derivative of this sine series exists, and wherever it exists, it equals -1. That is a kind of a little bit exotically looking result. And now I want to actually recall the function that I just, presented as a kind of generalization, natural extension of Riemann's function, non-differentiable function. Actually, you know, it is now a function of two variables, and we can actually look on this function as a function of two variables, t and x. By the way, this approach makes many things even look simpler in the sense of proofs. And I decided to study where does this thing come from. But running a little bit ahead, let me mention the following thing. I'm not completely sure that, but this is true already. If instead of the exponent 2 here, Riemann took the exponent 3/2, then the result would be already true, you know. That definitely the derivative of such function, or if I take any alpha smaller than 3/2 in the denominator, the derivative really would not exist at any point t. So a little bit of correction of these exponents, already takes us to correct result in this direction. Now, what is typical for functions like that? Let us consider the following sets of rational points on the plane. Actually, everything is, of course, determined, you know, by arithmetics of the parameter t. It's time parameter in the Schröedinger equation. And let us consider the following cases. The following actually grid on the on R2. That's the formal definition of this set of rational points